Great to be here. Actually, I was here once before in 2001, so it's a long time ago. But why I mention is that I talked about exactly the same thing. And yeah, there was like the second conference ever that I went to. The talk must have been pretty lousy. Thank God they didn't tape it back then. But yeah, and then I decided to never speak about this again because it was just too technical and I didn't like it. But I changed my mind, I guess. Okay, so what I want to do here is I want to consider Fourier coefficients of meromorphic Jacobi form. So what I'm going to do is I'm going to introduce the problem, then I'm going to give you the solution, and then after that we're actually going to talk about a little bit of motivation. So maybe that's the wrong way around, but that's what I'm going to do. So fortunately, we've seen most of the things that I'm going to, most of the objects that I'm going to talk about we've seen in one form or the other already, so that's good. So here I've just repeated what a Jacobi form is. We saw that on Monday, we all know it, but here they are again. So Jacobi form is a function in two variables, an elliptic variable and modular variable, tau. And it satisfies these nice transformation properties. So the first one is what I call the elliptic transformation property, shift by lattice points, lambda tau plus mu. Lambda and mu are integers, and it whoa, okay. If you look, if you set lambda to be 0 and mu to be 1, then it's just saying the function is one periodic. And if you set mu to be 0 and lambda to be 1, then it's kind of quasi-periodic. You get some extra factor. Okay, and then there's some modular transformation property. It reminds us a lot of the usual modular transformation property for modular forms. And yeah, I know before somebody is going to complain, I have the annoying habit of always writing the elliptic variables first, but yeah, it's just a matter of preference. That's because if I use elliptic transformation properties, I usually don't write the tau, and it's easier to not to skip the last part than it is to anyway, okay. But that's the convention that I'm going to use here. So this is important for us today. So if whenever I speak of a Jacobi form or I just write phi, it's always going to satisfy these, period. So m, there's some two integers in here, m and k. M is called the weight, k is called the index. The other way around, sorry. And those are always, I assume that we have those. Okay, but then for a Jacobi form, there's some extra conditions you want, classically, so usual. You want that they're holomorphic in both variables, and there, of course, there's always some growth condition. Today, I'm completely going to ignore the growth condition. I'm only interested in the transformation properties, and we're going to loosen the holomorphic a little bit. That's the idea. So forget about the growth condition, we don't want that here, and we're always assuming we have these transformation properties, but we're going to look at slightly more general functions by not requiring that they're holomorphic. And so here's a classical result that we all know. I assume we have also seen it on Monday. If you use classical Jacobi forms, you always have a nice theta decomposition. So that means it's phi. You can write it as a finite sum, L modulo 2m, where you have these classical theta functions. I think we had them explicitly as well. And there's some coefficients, which I call HL here, and they're given by this explicit expression here. And if you look at what this says, this integral just means that you compute a Fourier coefficient. Remember, in a z variable, it's one periodic. It means it has a Fourier expansion. And what you're doing here is you're just computing the Fourier coefficient. And this extra factor is just for convenience, because then theta decomposition looks as nice as possible. Okay, so that's classical. You can always do this. It's really easy to prove. It's not deep. I mean, it's one periodic, so it has a Fourier expansion, so you have the Fourier coefficients. If they're not gone, what happened here?
So easy, you don't need performance.
Is it? I should put it on. Uh, it is on presentation mode. Okay, maybe I speak too slowly, and I should skip my way through all the slides. Where was I? Okay. Oh, I was proving it. So it has a Fourier expansion. You call the Fourier coefficients like this. You call them H, and then the quasi-periodicity in tau. That just gives you a relation between the coefficient HL and HL plus 2m. So that means there's only 2m free variables, and if you work that out explicitly, you immediately get this. So it's really not deep, but it's kind of nice. So it kind of says that the elliptic transformation properties in the z variable, that kind of already determines it quite a bit. I mean, the only freedom that we have is in the HL, which only depends on tau. And that means these theta functions, they actually also have some modular transformation property. So if you also use the modular transformation property, for this you really only need the elliptic ones, not the modular ones. But if you now also use modular transformation properties, these thetas, they satisfy some sort of modular transformation property. So if you work that out, that means the HLs also do, and they transform like a vector value modular form. As I said, you only have 2m of them. If you put them into a vector, it transforms nicely. So here's explicitly, if you shift by tau, if you shift tau by 1, you just pick up a vector, and if you do the inversion, then you get a linear combination of all of them. So that means as a vector, it's a vector valued modular form with a very explicit transformation property, which comes from the transformation property of the theta function. So this is all the classical case. So I said I want to generalize this, so we're going to consider meromorphic Jacobi forms. What is a meromorphic Jacobi form? Well, it's kind of almost the same, except that I allow poles in the z variable. Meromorphic. It's allowed to be meromorphic in the z variable. Why? You might think, well, it's a generalization. Well, actually, at that time, I was a PhD student, and I was supposed to do something on Mach theta functions. And it turned out in literature there were identities which relate these Mach theta functions to Fourier coefficients of meromorphic Jacobi forms. Actually, it's a theta quotient, but that's a typical example. But I'll speak about that later on. So one way of attacking the problem is to look at Fourier coefficients of meromorphic Jacobi forms. So we look at we allow poles in a z variable. That's it. In the tau variable, it's still holomorphic. I don't require a growth condition, so it's actually weakly. It could blow up at poles. I don't care. I don't care. So Fourier coefficient, you can still define them in the same way. This is exactly the same formula. But now, of course, it depends on the choice of p. The base point, we integrate from p to p plus 1. If I shift that, yeah, you can compare them, the two expressions, by considering contour integral, but you might pick up poles. There might be a pole in there, and that means the Fourier coefficient is going to depend on the choice of p. But I'm just going to assume that we have picked some p, some nice p, and we can always consider the Fourier coefficient. So the p is then fixed, and then we consider it for all the Fourier coefficients in the same way. Right, okay, so a typical example, as I said, is a quotient of theta functions. So I want to show you that, how that would look like. So just to remind you, we saw this on Monday, the classical Jacobi theta function. It was defined like this. It was in Niels' talk. We all remember that one. And yeah, that's basically an example of a Jacobi form, except that you have like a multiplier. It doesn't quite satisfy these transformation properties, but almost up to some extra constants. And if you want to look at the zeros of this thing, that's really easy. Zeros in the z variable. I'm always speaking about the z variable, the elliptic variable. It's in lattice points, z tau plus z. Here in this, if you write in terms of q and zeta, it's if zeta is an integer power of q, then you get zeros. And no other zeros. You can see that from this nice product expansion here. You know exactly where the zeros are. So if you want to come up with a meromorphic Jacobi form, you could consider, for example, something like this. So I've just taken a theta quotient and you put some theta functions up here, you put some theta functions up there. And well, if you shift the z variable by such a thing, it will still, and multiplied by the right power, it will still be a Jacobi form, maybe on a subgroup or something. But so in general, this is not going to be on the full modular group with exactly the transformation properties that I showed you, but for suitable choices, it will probably be. But a typical example will look like this. And even I'm in this talk, I'm only speaking about the transformation properties on the full modular group, but you could, in principle, also consider subgroups or multiplier systems, whatever. It should still all works the same. So this is a typical example. And what are the poles here? Well, the poles come from the zeros of the theta functions down here. We just establish what the zeros of the theta function are, so that it immediately tells you what all the information is here. So this has, Niels explained that the theta function has index 1/2. So this thing in total has this index. The weight, theta also has weight 1/2. So yeah, this is coming from the theta quotient. And then, yeah, because I didn't say anything about the Tor variable, I could always just multiply by something weakly holomorphic or whatever, and that would increase the weight by k. And the poles are potentially in this set. So this is these lattice points, and we've shifted them because of this shift. You shift them. I say potentially, of course, because yeah, it could be that the zeros of here also show up as zeros of here, and they would cancel. Potentially, you have poles in this set. So this is a typical example. So for the mock theta functions, it kind of looked like this. And so the question is, what are the Fourier coefficients of such objects? Are they again modular forms, or maybe something more wild? And of course, yeah. Yeah? Oh, because you shift by this, and then in general, it's not going to be a Jacobi form anymore. You have to multiply by suitable rational power of q to get that. That's why. Yeah, of course, we know the answer is probably going to be something mock, right? So, indeed, that is true. So, yeah, now comes the technical part. This is why I don't like speaking about this. So, in order to formulate it, I first have to give 3 definitions, and then, oh well. So I'll just give it a shot. So I'm going to formulate the result, what this thing actually is, and I need a slight generalization of the usual notion of a residue, because we're going to consider here functions which are not always holomorphic. We're going to look at some real analytic functions, and so you want something like a residue. So here, what do? I have a real analytic function f, so that doesn't have any singularities, and then I multiply it by a meromorphic function g, so that is complex differentiable, but it does have poles. And now you want to say what the residue is of the product f times g. And of course you can, because of the conditions that I put on f on g, you have an expansion like this. Here the index n, that's positive because I required f to be real analytic. It doesn't have poles, but in here the power can also be negative because we allow g to have poles of order s. Did I say s? Yeah, of order s. And so I define residue just by, I take one of these coefficients, just as you usually do for the residue, namely coefficient -1, 0. And if you actually want to compute that thing, it's easier to work with this expression. You multiply this product f times g with v minus u to the power s, and you differentiate. This is then the holomorphic derivative. Differentiate that a couple of times, and there you have your coefficients. So, and of course, if f has to be, if s turns out to be holomorphic, this is the residue, of course, the classical residue. Okay. Yeah. So that's one ingredient to state the things. I also need this definition. So as of Tor, I let that be the set of poles. That depends on Tor, so that's why notation Tor. We consider it as a function of the elliptic variable, and we just look at where are the poles. That's S of t. We had this base point P, where we integrate from P to P plus 1. So I also need a fundamental parallelogram, which I denote by PP. So that's for a fundamental parallelogram with base point P. And then sometimes it's convenient to only consider the poles inside such a fundamental parallelogram. So for this, I set this SP tau, which is the set of points inside such a fundamental parallelogram. And for the lattice, zeta plus z, I use shorthand notation lambda tau. Okay? And now comes more definitions. Now comes the answer, basically. So what I did here is, so these HLs, that's a Fourier coefficient. The one that we defined earlier, the one that we really like to study. And as a function of tau, this is holomorphic. And the idea is, I'm going to add something to it, such that now it becomes modular. In general, it's not modular, but we're going to fix that, we're going to correct it. I'm going to add something, this whole thing, and yeah, then it becomes modular. That's a statement, that's on the next slide. So this is what you usually see in the mock business. You have some interesting function, which is holomorphic, but you want to turn it into something modular, and that's why you have to correct it in some sense. And so it turns out the right correction is this whole expression here. So this is my original Jacobi form, the meromorphic one. This is my real analytic function, which I defined here. Well, that looks really odd, but if you know anything about mock modular forms or mock theta forms, you've probably seen something like this before. It's a very explicit function. That's the whole point. It looks ugly, I agree, but it's very explicit. And in a sense, it's actually not so bad. It's actually nice. But okay, anyway. So here's then, you take a residue, as we've discussed before. You can do that. All the conditions are satisfied. And you just sum. This is a finite sum. You just sum over the poles inside this fundamental parallelogram with base point P. This is bad notation, maybe, because the HLs, they also depend on P, but that's not in the notation. So, but I always assume there silently that it's at P. Okay, so what is the idea? This thing, this corrected one, HL hat always means that we've corrected it. That is really going to transform like in the previous case. So we've corrected it, and then, ta-da, you have the old formulas back. So you had to do some correction, but then they transform nicely. They transform as a vector valued modular form of weight k minus 1/2, just as before, and the transformation properties look exactly the same. So the few remarks, where shall I start? I put a question mark here, so you see this is pretty old. Maybe I'm getting old. I put a question mark. It never appeared in a journal, so I'm not sure if it actually counts as a real theorem. I only wrote it up in this little green book, but yeah, oh well. That's it. And yeah, actually I do like this result because it's the formulas might be a little bit ugly. I'm going to go back so you can appreciate the ugliness, but it's pretty general, because I didn't put any restrictions on the poles. The poles can be anywhere, orders can be anything. There's absolutely no conditions there whatsoever. So any meromorphic Jacobi form, this tells you exactly what to do. In general, it's pretty ugly, but it's quite general. So that is actually nice about this. It kind of solves it for the general case that I consider here. Okay, so let's look at an example, maybe that's better. So it is so ugly because it's general. But if you look at special cases, then it might actually not look so bad. So here, as an example, I consider meromorphic Jacobi form phi such that it has only simple poles, and I assume that it only has poles in this lattice. So that's basically as simple as it gets. as simple as it gets. And I take P to be like this. And then that means inside the fundamental parallelogram, there's only one pole, and it's located in 0. So you can work out what the formula says. You have to take a residue, but it's really easy here. And it says this correction term now just looks like this. It's just, there's no sums anymore. It's just one product of two things. This function d tau, which is just the usual residue of your meromorphic Jacobi form at 0, which is just an ordinary modular form of weight k minus 1. So that's a nice thing. This is something we all know and love. And then you have to take a product with this new ugly thing, RML. But what does that mean? What does this do in terms of the mockness? This is what you would call a mixed mock modular form. You've seen that already once or twice. What does that mean here? I'm going to speak about this a little bit more in detail later on, but this is what you would have in this case. It means that if you take the mass lowering operator, this L is the mass lowering operator. We've seen that before. We've seen it like this. We've seen it with 2i times this. Yeah, it's almost the same. If you apply it to this thing, you get, well, the D is holomorphic, so that doesn't change. And if you apply the mass lowering operator to this, you actually get something classical again. Namely, we have a theta function of this type, and the only thing you have to do is you take a complex conjugate. So these objects are classical. We all appreciate those. The D is just a holomorphic modular form, and here we have a holomorphic modular form, but you have to take the complex conjugate. So this is what you would call a mixed mock, because it's a product of two things, and that's why it's mixed. In general, you allow finite linear combinations of such objects, but here you only get one of them. Okay, so how does the proof go? It's actually, once you have formulated the final statement, it's actually quite easy, almost. It's just some complex analysis. You do some contour integrals, and the whole point is that you can then find a decomposition of your Jacobi form in terms of the upper Lerch sum, which we've also seen. And then if you know how you can correct the modular transformation properties for the upper Lerch sum, then you know how it works for the whole thing. So that's basically the idea. But I definitely don't want to go into details there. Okay, I'm doing good. I'm halfway, and I'm halfway through my slides. Okay, so now a little bit of motivation. As I said, for me, personally, the motivation was these mock theta functions. I just wanted to understand those, and this is one way of attacking that. And the theorem tells you exactly how that works. It doesn't directly apply, because the Jacobi forms there were on a subgroup, and you have some characters. So you can apply directly, but you could, in principle, use that. I didn't, but it should work. It does work exactly in the same way. So that was enough motivation for me. But then later, other people also found applications and improvements. So I should mention the work by these three people. For example, they used some of that and they made some improvements. So remember that everything depended on this base point, and they made a smart choice for that, and they let it depend on the L, and then you can nicely decompose the Jacobi form, etc., etc. So they made some nice improvements on the level of Jacobi forms. Since I'm not doing that, I'm only looking at Fourier coefficients. I don't have to discuss that here today, I think. And yeah, so also another application where this was used is Kac-Wakimoto characters, because, well, what the interest therein is, I'm not going to tell you what Kac-Wakimoto characters are. That's something coming from representation theory. But then in the end, what it boils down to, they just have a very explicit quotient of theta functions, and these characters are the Fourier coefficients. So that's exactly the thing that we did here. So Amanda and Catherine, they they did similar things in case of the Kac-Wakimoto characters, and they studied the modular transformation properties, kind of similar to what we did here. And they found that in this case, the Fourier coefficients are the holomorphic parts of vector valued almost harmonic mass forms. Okay. That was then generalized. Here, in the case of Kac-Wakimoto characters, the poles are only in the lattice points, not more. You can generalize it, of course. So Olivetto, a student of Catherine, he generalized this. He looked at the general case for poles, and he found the same results. So he found that it's the, what is it again? The holomorphic part of a vector valued almost harmonic mass form. So here's the definition. That's not my definition. I just took it from the paper by Olivetto. So it's again, yeah. Again, the question is what to think of this. So in one sense, it's ugly because it's a finite linear combination of sums of this form, where you take a finite sum of a product, etc., etc. But the good news is that the ingredients, that is all things that we know and that we're familiar with. So here in this, what is all of this? So these G's, that's just, they're almost holomorphic modular forms. We've seen those. I'm not going to go into the discussion if you should call it nearly or almost. In this talk, I'll just call it almost. That's the G's, and here we have an F, and that is harmonic weak mass form. We've also seen those. And then you're allowed to take a bunch of times the mass raising operator, R. We've seen that one. And then, of course, now the weights all have to match, or you have to do it in a specific number of times, and then in the end you end up with something of weight K. But so it looks complicated, but the ingredients are all stuff that we know and that we're familiar with. Okay, so that's good. For me, this is not, for me personally, I'm not really satisfied with this definition, but that's what it is. So actually, I think of these things a little bit differently. So that's what I would like to discuss now briefly, and then I give some examples of that, and then we try to also put these Fourier coefficients of meromorphic Jacobi forms. I'm going to try and put that into the same picture. So this is more this kind of philosophy what we're doing here. So this is how I personally think of mock objects. Because as somebody also, I forgot who it was, but somebody remarked that in this whole business with modular forms and mock modular forms, there's a lot of adjectives that you can add. So we have so many adjectives by now. During breakfast on Monday, somebody suggested that we should consider the algebra generated by all these adjectives. And study that. I don't think it's commutative, for example, so you could consider quasi-mock or mock-quasi, and then, okay, but anyway, so I'm not going to do that today, no. But I do want to say something in this direction. So for what is for me a mock modular form in generality, so with some adjectives added. Well, the key point here is that we have the mass lowering operator, L. Here it is again. And what are the nice properties of this thing? Well, it preserves modularity. That's one. And it lowers the weight by 2. So what does that mean? If you have an object, real analytic, which transforms as a modular form of weight k, and you apply the mass lowering operator, you still have something which transforms as a modular form, but now weight k minus 2. So all modularity is preserved. It just lowers the weight by 2. And further, that's clear because here it says the anti-holomorphic derivative, it immediately kills anything that is holomorphic. So anything that is holomorphic, it completely disappears immediately. Okay, so now comes the thing. So let's say that I have a function f hat. I put in the hat deliberately, so that's going to be similar to the f hats that we had before, the completion. That's the object that is not quite holomorphic, but it does transform like a modular form. So let's assume we have such a thing. You apply the mass lowering operator, and you get a function g. Right? Now let's assume that I only give you g. I don't tell you what f hat is. I only tell you what g is, and I tell you I want to find a function such that the Maass-Lowing operator applied it gives you exactly g. Well, what can you do? Well, of course, you can always use the technique which I call naive integration. You just integrate. What can you do? You just divide by this, and then you take an entire holomorphic derivative with respect to tall bar, which you can probably do. But of course, the downside is this kills all modularity. But you can do it. You can write something down, probably, so naive integration, and you come up with a function, g star, such that indeed Maass-Lowing operator applied to g star gives you back g. So you did your job, you did your homework very well. And now if we're going to compare the function f hat that I had and the function g star that you had, mine is better because it's modular, yours is probably not. But if you look at the difference here, f hat minus g star, because they both give the same thing, when you apply the Maass-Lowing operator, that means the difference is holomorphic. It's killed by the anti-holomorphic derivative. So it's holomorphic. So up to something holomorphic, you've done a pretty good job. So that's it. We now have a holomorphic function. And that holomorphic function I would then call a mock object. So I call it a definition because, yeah, it's a bit vague. I don't tell you how to exactly use naive integration. There's a word nicer in here, which also is not so clear what exactly that means. So what is my definition here? So I'm assuming I have such a modular object, f hat. I look at the corresponding g, which is the Maass-Lowing operator applied to f hat, and I want it to be nicer than the thing that I started with. It should improve things, in some sense. And then you can do what we did before, naive integration, and you come up with a holomorphic function f. So that's, you can always do that, probably. And this function f is then the holomorphic part, in some sense of f hat, and I call it a general mock modular form. So this is general because I don't require too much. I just want things to be nicer. Okay. So that is the framework in which you can see a lot of these mock objects. And the point is, just as we know for mock modular forms and all the variations thereof, the nice thing is that this holomorphic part is of course holomorphic, but it's not quite modular. We have to add this g star to it such that it becomes modular. G star is the correction term. You could call it g, you could call it the shadow, although it doesn't really on the nose correspond to what we know as the shadow. But yeah, so it's holomorphic, not quite modular, but its non-modularity is measured by g. If I have g, you can always construct g star by naive integration, and then that tells you exactly what to add. So up to g, you know exactly what its modularity is. And or the other way around, you could consider f hat. That is also nice. It's modular, but it's not quite holomorphic. Well, what is obstruction to holomorphicity? Again, that's g or g star. Okay, so it's two sides of the same coin. You can always decide, do I want to consider f, do I want to consider f hat? And they both have nice things, and they both have something which is not so nice. Okay, so let's look at some examples here and try to see how that fits in. So here, again, almost holomorphic modular form. I just took one of depth d. My definition of depth is slightly different than what Martin discussed about. For me, the depth is just the degree of the polynomial. So he defined, or almost holomorphic modular form is defined as a polynomial in 1 over y with holomorphic coefficients. And the degree of that polynomial I call the depth. So that means that fd, the highest coefficient, should be non-zero. Okay, but it doesn't really matter here. I call it f hat. Yeah, you can guess why, because then it exactly fits. So what happens if you apply the Maass-Lowing operator to this? It's just taking the derivative. It's just, well, it is, you can just do it immediately, explicitly. It's a really easy exercise. But if you look at the formula, what it means is you just take the derivative of the polynomial, basically. So you just take the derivative with respect to 1 over y. So what does that mean? It has the same form. It's still modular. So that means it's, again, almost holomorphic modular form. Nothing changed there. But the depth has gone down. It's now the polynomial of degree g minus 1. So in that sense, it's nicer than the things that we started with. The depth has gone down. It's less complicated. It's less deep. So that's what, in this context, that's what nicer would mean. And then we can do the naive integration. So as I said, what if I would just give you this thing, and I would tell you that you have to find something such that the Maass lowering operator applied to it gives you back this thing? What would you do? Yeah, what you see here, you lost F0. That just dropped out. All the other Fs are still there, only F0 somehow got lost. So all the information is still there. You can reconstruct it except for F0. You have no idea what my F0 was, right? I didn't tell you that. So you can, if you would just do naive integration, you would get the same thing, but you don't know what F0 is. So you can't include it here. But this is the information that I have, all the other FLs. So that's, in this sense, that would mean naive integration. And that indeed satisfies the condition that the Maass lowering operator applied to this exactly gives you G back. And then the holomorphic part is the difference of my function and the function that you found. In this case, that's exactly F0, and that is, of course, holomorphic. So F0 is the holomorphic part of this almost holomorphic modular form. So the constant term, it's a polynomial, it's a constant term, but it's weird to call a function a constant term if it's not, anyway. So it's a constant term in the polynomial, and actually classically you call this a quasi-modular form. Constant term of a almost homomorphic modular form. So the point of showing this is that it fits into this philosophy that I just tried to show you. The original modular forms, of course, they fit into the same picture, otherwise it wouldn't make sense. So let's briefly discuss that one. So let's assume here that f hat is a harmonic weak Maass form of weight k. We've seen that in Jensen's talk. What is a harmonic weak Maass form? It does transform like a modular form of weight k. It's not quite holomorphic, but it's annihilated by the hyperbolic Laplacian, which is second order differential operator. You can write it, you can interpret it like this. So this is a restatement of the fact that it's supposed to be annihilated by the hyperbolic Laplacian. So what do I do here? I take my function, I use the Maass lowering operator, then I do complex conjugation, multiply by a suitable power of y, and then do the Maass lowering operator again. Yeah. And that should then be 0. It should be annihilated by this. But you can interpret it in a different way. If the Maass lowering operator to this whole thing is 0, that means that thing is what? Is holomorphic. So, and if you then divide by this and do complex conjugation, that means that the Maass lowering operator to apply to f hat has to be of this form, where G is holomorphic. And actually, since all modularity was preserved, it's modular of weight 2 minus k. Yeah, this is the usual statement. Usually it's formulated in terms of psi. Psi is where you do the Maass lowering operator and then you do complex conjugation, and then you get a holomorphic modular form. So it's exactly that statement, except that I put the complex conjugation on the right instead of on the left. So yeah, I'm cheating here a little bit. Before I called the Maass lowering operator to an f hat, I called it G. Here I use G in a slightly different way, but the philosophy is still the same. And you can do naive integration here. If I just told you y to the 2 minus k g bar, find me something, you could do this. This is naive integration. You just divide by y to that power, and you take an antiderivative in the tall bar. You can immediately see that this G star, if you apply the mass lowering operator to it, you just take a derivative with respect to this. If you plug it in, you immediately get G back. So this is what would happen if you do naive integration in this case. And then the same thing as usual works. You can consider the holomorphic part, f hat minus G star, and you call that a mock modular form, a classical mock modular form. So that works here, all right? As we've briefly mentioned mixed mock modular forms, so mixed is one of the adjectives in our algebra. Yeah, what happens there is that if you have an f hat again, you apply the mass lowering operator, and you want it to be nicer, but here allow more. So you take, this part is what we had on the previous slide, but now you allow that you multiply by a holomorphic modular form, and you allow that you take linear combinations of this. So the sum of J means I take a finite linear combination of products of this type. So the first thing is a holomorphic modular form, the second thing is like in the previous. So it's you allow a little bit more. And it's mixed because you have something holomorphic and the complex conjugate of something holomorphic. That's why it's called mixed. Yeah, the same thing works. You could, what about naive integration? These things are holomorphic, the anti-holomorphic derivative doesn't see it. So I could just do naive integration on this thing, and the star here means the same thing as on the previous slide. This exactly gives you then a pre-image. If you apply the mass lowering operator to this, you get exactly this expression up here. And then you can consider the holomorphic part, and you call that a mixed mock modular form. Okay, fine. So why on earth am I telling all this? Because I also would like to interpret the Fourier coefficients of meromorphic Jacobi forms, for which we've seen explicit formulas. Here they are again. I want to interpret that in the same setting. So I would like to propose a slightly different characterization of these objects. So this is just to remind you what did we do? We had this meromorphic Jacobi form phi. We look at the Fourier coefficients. We call it HL. That's the holomorphic object. We corrected it. We added this thing. That's real analytic. But the good news was we ended up with a hat object that is modular. So how does it fit in to what we said? What do you have to do? Compute the mass lowering operator of this, right? And that should then be nicer in some sense. So let's do that. I just want to apply the mass lowering operator to this and see what kind of objects that you get then. And if that's nicer, then it indeed fits into this picture. HL is then the holomorphic part of HL hat. And yeah, the non-modularity or non-holomorphicity is characterized by mass lowering operator applied to this object. What happens if you apply the mass lowering operator? You can do everything explicitly. There's nothing really difficult, you just do it. These things are immediately killed because it's holomorphic. That vanishes immediately. So you have to take the mass lowering operator of this thing. There's a residue here, but that's kind of we formulated it also in terms of derivatives, and you can just swap them basically, and then you only have to apply it here. But this is holomorphic in Tor, so that's also fine. So in the end, what you really have to do is apply it here, basically. Yeah, so you can just do that, and so I did that, and you get relatively nice objects. So that's the last example that I would like to discuss here, what happens explicitly in this case. So to formulate that, I need a couple of definitions again. These are not so bad. Things become really nicer if you apply the mass lowering operator. All the definitions and objects that we see here are classical objects that we all know and love. So we already saw this one, the theta function. We needed that in the theta decomposition. So that's just to remind you. We need a slight variation of that. I plug in an extra polynomial of degree 1. That means we raise the weight by 1. So this is essentially, again, a Jacobi form, but because there's the imaginary part here, it's not holomorphic, it's real analytic, but it still transforms like a Jacobi form, but now in weight 3/2 and index 1/2. I want to look at these things in torsion points, in points alpha tau plus beta. Alpha and beta are rational. So to accommodate for that, you have to multiply by suitable power. Don't worry about that. So this is just the same thing, but you multiply by a suitable thing. Because then, if you do that, if you specialize U, what I call U here, if you specialize that to such things, alpha tau plus beta, where alpha and beta are rational, then this actually transforms as a modular form. That's a classical result. That's in Eichler-Zagier. They say that if you take a Jacobi form and you specialize to a torsion point, it transforms like a modular form after you have multiplied by the right thing here, and that's exactly the right thing. We were speaking about mistakes in Eichler-Zagier the other day. There's also a mistake in that statement. A group. It says here, it's not on full modular group anymore, it's on some congruence subgroup, which depends on alpha and beta. Note that the group that they give, there's a few sign errors, but okay, just doesn't matter. There's an explicit group. And so the first one, this one is weight 1/2, second one is weight 3/2. Right, so I said, what happens if you apply, we want to see what happens if you apply the mass lowering operator to the objects that we discussed. Well, it does get simpler in some sense. So here I do have to assume something about the poles. So it's slightly less general. I have to assume that all poles are of this form, alpha tau plus beta, where alpha and beta don't depend on tau. In the case of the quotient of theta function, that's a condition is automatically fulfilled, so it's not that much of a restriction. And in most of the examples, this is the case, so you don't lose that much. But then this statement says something that if you apply the mass lowering operator to these objects that we found before, you get, this. So it's not so bad, maybe. So here, these are these objects. This is the holomorphic modular form of weight 3/2, and you take 3/2, and you take the complex conjugate. Here, this was weight 1/2, you take the complex conjugate. And there's some there's functions here showing up. So this looks very much like the mix-mock case, right? Well, except that these extra functions, they're not holomorphic, but they're almost holomorphic. Okay, so I say behave like an almost holomorphic modular form because for almost holomorphic modular forms you also impose a growth condition, which I always ignored here, so I also ignore it here. But these behave like almost holomorphic modular forms, and everything is explicit. So you know what the weight is, you know what the depth is, etc., etc. The depth depend on the order of the pole. So if you have really bad poles, that means you get really bad almost holomorphic modular forms. They have high depth. But it's a finite sum. This is just a finite sum. You sum over all the poles modulo the lattice. So that's a finite number in your fundamental parallelogram, and you can just compute all these things. And it's
what is the smiling?
That's the theta. Oh, sorry. I used the notation with a dot before. That means up to constant. With two dots, it means up to two constants. So there should be some constant here, and there should be some constant here. It's sloppy, I know, but I've...
But really constant, which does not depend on tau, or...
Yeah, it's just the square root of m times pi or whatever. But the other constant is slightly different. For the presentation, it's nicer to just ignore them and send it to 1. Okay, but yeah, but actually I have 10 seconds left, yeah, okay, so let's look at an example. So we saw it was interesting to do this for the Kac-Wakimoto characters. They were simpler because there were only poles in the lattice points, not more. That means the sum already reduces to just one term. And then you can consider if the weight is even, Yeah, then that actually means that the Jacobi form is even, and that means that the order of the pole has to be even, and you just get this. That's one of the terms immediately drops out. The finite sum is only one thing, so it's just one simple product of complex conjugate of a theta function, and you have this almost holomorphic modular form. If k is odd, it's exactly the other way around, and s is odd, the other term drops out, and you get this thing here. Now you have, this was weight 3/2, in this case you have weight 1/2. So it reduces, and this doesn't look so bad, right? So that's nice, maybe. Yeah. So that's basically what I wanted to talk about today. In the
You have one page more.
basically what I wanted to talk about today. Yeah, it's only 30 seconds or something. In my abstract, I promised that I would also like to discuss negative index. Here, the index was always positive, but I wanted to also discuss negative index. And Larry promised that yesterday that I would speak about it today, but I didn't feel like it. But so I just included one slide. Just quickly. You can also look at negative index. But there's, in holomorphic case, there's nothing. There's no negative index holomorphic modular form. So there's nothing like theta decomposition. In the holomorphic case, it's completely uninteresting. But meromorphically, you can do that. If you have more theta products at the bottom, then it's going to be above. Then that means it's going to be negative index. So you can still consider those. But actually, once you have the final statement, I found it to be really boring, and it's much easier in some sense. The formulas become much easier, but yeah. So what is the picture? I think Larry also mentioned this yesterday. So we did that first. It was by Catherine and Larry and Kac, and then in a special case where you only consider poles and lattice points, but then we figured out how to do it in a general case. And the result is, I'm just going to write it down, the Fourier coefficients are finite linear combinations again, of products of quasi-modular forms with derivatives of partial theta functions. Okay, we've seen all the ingredients. It's not so easy to interpret it in terms of modular things. If you want to interpret this in terms of modular things, you would have to go to quantum modular forms. You can interpret this as quantum modular forms. So you say here you take derivatives of quantum modular forms, you multiply them with quasi-modular forms, and then you take suitable combinations. So you can do it, it's explicit, but I found it to be less inspiring. But anyway, okay, so it's a risk. Yes, and that's what, now I'm really done.